So student t-distributions are very important in statistics, but what do they actually mean? You probably heard that they're a family of curves where we've got t1 where they're defined by the number of degrees of freedom, where we say the number of degrees of freedom, use the symbol nu, is equal to the sample size n minus 1. So here's a t-distribution with 1 degree of freedom, and then here's a t-distribution with an infinite number of degrees of freedom. So this would be like taking an infinite number of samples, for example. And as it turns out, that the larger the number of degrees of freedom, the closer these things get to a normal distribution. So one question I've always had are where do these distributions come from, or what do they mean, or what can we do with it? So in a book, we'd say you could look up that they often say that the ratio, the sample mean minus the population mean, divided by the sample standard deviation s divided by the square root of n is t-distributed. And as the number of samples gets larger and larger, we start out with a sample size of 2, and a sample size of 3, for example, if I crudely drew another curve in here, would look something like this. And as the sample size gets bigger, the t-distributions become more and more normally distributed. And one thing to take away from this as well, one thing to pay attention to, is that the width of the tails in the t-distribution becomes shorter and shorter. And that's really important later on when we use the t-distributions for statistics. And to try to figure out where these distributions come from, I've developed some simulations where we can see how they naturally arise. The first thing that we need to assume is that all of the samples or all of the measurements that we're collecting come from a normal distribution. So in this case, for this, we have on the x-axis is whatever we're measuring. This could be weight, for example, in kilograms. If we were dealing with circuits, it might be amperage or voltage, or if we were pulling parts apart, it might be the breaking strength in newtons, or maybe chemical conversion if we were doing some chemistry. But the x-axis here is measured in whatever appropriate units you're working with. And for my simulation, I've elected to use a population mean of 12 and a sample or a population standard deviation of 2. In this simulation, I have a sample size of 2. So I'm going to collect one sample of 2 measurements. And what I'm showing here is in the red line is the sample mean, and the 2 x's at the bottom are the 2 values of the sample, and the width of that horizontal bar is the sample standard deviation. And in my simulation, let's collect another sample of 2 measurements, and another one, and as I keep running through this, one thing you'll notice is that the sample mean will change. The red bar moves left and right, but so does the sample standard deviation, and this depends on how far apart the samples are from one another. So here we see a small sample standard deviation. Here's a relatively large one. And for each one of these simulations, I can calculate a value for t. So here's a simulation in which I collected one measurement, and that value was 8.59 for this one. And for this one, I collected a measurement randomly of 12.61. And the average of these two is my sample mean, so x bar is equal to 10.60. And I also calculated the sample standard deviation, which is s. And for this one, s is equal to 2.85. So let's calculate a value of t for this simulation. It's the sample mean of 10.60 minus the population mean of 12. I'll get a negative value for t, divided by the sample standard deviation of 2.85, divided by the square root of n, the square root of the sample size of 2. When I calculate this, I get a value of t of negative 0.695. So from here, what I'm going to do is run multiple simulations, and I'm going to collect multiple values of t, and I'm going to make a histogram of all of these values of t. So here's my simulation. I'm showing the exact same normal distribution on the left, and what I'm showing on the right is a t-distribution with 1 degree of freedom. So I'll run my first simulation. And what I've computed are I collected 2 measurements, so one sample, here's my sample mean and my population mean, so I'm going to get a positive value of t, and here's my sample standard deviation. So here's my value of t right here, and I'm making a histogram of all my values of t. So I'll run it again, and I get another value of t, it's negative in this case, And as I make multiple runs, I start collecting a histogram. And what I expect is over a long period of time, or with sufficient number of iterations of this, I'll eventually build up to a t-distribution, or what we would expect. So as I continue running it, I'll run it 300 times, for example. And this is like running 300 different experiments, collecting 300 different measurements. And what I see is something that begins to look like a t-distribution. Note that one thing that we observe are the width of these tails for a small degree of number of degrees of freedom. And the reason these tails are so much wider than they are in a normal distribution is because the sample standard deviation can also vary. So the sample standard deviation is in the denominator, and a small value for sample standard deviation tends to push our value of t off to the left and off to the right. So what I'm going to run now is a simulation. We'll still have each sample size will consist of 2, but I'll run it a whole bunch of different times. I'll run it upwards of 10,000 different iterations on this. And when I run the simulation, what we observe is the buildup of the distribution of t-values that eventually reaches a t-distribution with 1 degree of freedom, which is a sample size of 2. Or if I want to run it even more precisely, here I'm running a simulation with 1,000,000 iterations. So 1,000,000 samples with sample sizes of 2 measurements each. And we see once I run it with a large number of simulations, I get a very, very close representation of the student t-distribution. In reality, you probably will collect more than 2 measurements for your sample. Usually I would say 3 to 5 measurements or something like that would be more typical. So let's run this with 5 different measurements. And here I've calculated a sample mean that's just shy of the population mean, calculated the value of t for that, and put that into my histogram. One thing to pay attention to is now I'm showing the t-distribution with n-1 or 5 minus 1 equal to 4 degrees of freedom. You see how the tails for that t-distribution came in a little bit. And the reason for that is if I keep running these, take a look at the sample standard deviation, and they tend to be closer to the population mean simply because we've collected more measurements for one particular sample. So as I keep running this thing, the distribution of, or my histogram tends to approach a t-distribution with 4 degrees of freedom. And if I wanted to, I could simulate a case in which I collected 100 measurements for my sample. So I've got 99 degrees of freedom. There are my 100 samples on the left. And one thing, when I continue running this, look at how close the sample mean is in general to the population mean. And look at the consequence of that in terms of the t-distribution. I'm showing a t-distribution now with 99 degrees of freedom. How tightly those tails come in, mainly because the sample mean is so close to the population mean in general. So if I continue running this, I get a t-distribution with 99 degrees of freedom. And if I want to refine that simulation further, here's a simulation with 1,000,000 different replications of that. And I see it building to a t-distribution of 99 degrees of freedom, which incidentally is essentially a normal distribution. So for a very large sample size, we begin to converge to something that looks like a normal distribution on the right. And again, when I zoom in on this, I see very good representation of a t-distribution with 99 degrees of freedom, even way out in the tails. So the takeaway message from this is that this ratio, the sample mean minus the population mean divided by the sample standard deviation divided by the square root of the sample size, is t-distributed, and that has important consequences for other areas of statistics.